I'd like to congratulate school children and students on the upcoming academic year. And I offer you a small video about calculating the parameters of FlyBack converters for charging capacitors based on the UC, for example, 3843 or 2845. Here is the line of the chips. These are so-called current mode controllers, which are most suitable for such schemes. Let's go on. At first, I'll say a few words about how these converters work. I found a simple scheme in internet where it seems all the necessary elements are present. The UC chip controls the power switch using a sequence of rectangular pulses, the duration and the fill factor of which are set by this resistor and this capacitor. The switch through a transformer, in this case with the transformation coefficient of 1 to 1, and the rectifier diode charges our output capacitance. In addition, there is a current sensing resistor in the primary chain, the signal from which is caught by a current comparator, and when a certain level is exceeded in this pin, it prematurely interrupts forward cycle of the converter. In addition, I have depicted two states in which the converter can be the continuous current mode, so-called CCM. Here, at each moment of time, current flows either through the primary winding or through the secondary one. And the discontinuous current mode, DCM, which corresponding when a corresponding pause is formed on the oscillograms, so-called dead time. Okay. Now let's go directly to the calculator, and I'll tell you right away why I came up with it. The fact is that there are many different programs and scripts in the net for calculating FlyBack converters, which among other things can even determine the necessary parameters of winding products, for example, core type, number of turns, etc. But they have one problem. They describe the stationary mode of operation of the converters, i.e. with constant input and output voltage. Input and output. In our situation, the output voltage is constantly changing because a bulk capacitor is being charged. For the same reason, I was unable to use the LT-SPICE package. It perfectly describes and displays all the dynamic features of each cycle and works on the basis of SPICE models of components. It also takes into account parasitic elements, but in order to change a capacitor in, say, we can see, for example, here it takes 13 seconds and our period is 16 microseconds. So in our case it takes nearly 1 million cycles. It's a very long time if you don't have a supercomputer. Perhaps I didn't figure something out and the experienced users will tell me, but I still did not understand how to properly simulate the charging process of a large capacitor in LT-SPICE. That's why I had to simulate the charging process of a large capacitor with this calculator. In addition, I was interested in understanding how all the process take place and what formulas are described. By the way, I will not give the formulas themselves here. They are quite complex, and if anyone is interested, contact me. I will write anything down. Okay. What we have now. Here is the input parameters of this model. It's input voltage, on time, off time. Here is on time, off time. Summary time, it's a period. Frequency, it's inverse period. Maximum current set in the primary chain. Output voltage, you can see that it is changing constantly. Inductance of the primary winding of the transformer. Transformation coefficient. Here is all the way 2.9, as you can see, because it is related to the specific transformer I was studying at that moment. Delay time, it is time which corresponds to the delay between the voltage exceeds 1 volt on the current sense pin and the chip and the power switch are disconnected. So it's a sum of delay time of the chip itself and delay time of the power switch. And it's in my model it appeared to be about 1 microsecond. Okay, then we have dynamic parameters. Switch time, switching time of the MOSFET, of the diode. Then forward voltage of the diode. Maximum avalanche voltage of the switch. It's 5.5 volts now. Internal resistance of the switch. MOSFET drain source capacitance. Transformer winding resistance, first primary winding, secondary winding, and leakage inductance of the transformer. It's always constant in this model. Okay, now what is calculated? The calculated here is at first some additional parameters, so-called official maximum current in the primary winding, primary current limit. Here the fact that current limitation takes place is established. For now, we can see that in these parameters, according to these parameters, it is only unlimited in when output voltage is 1000 volts. In all of the cases it is limited. It means that maximum current is is equal to the effective maximum current in the primary. Then we establish the fact in what mode our converter works, DCM or CCM. Then we can see the maximum and minimum current of primary and secondary windings. These are these points. Timing parameters, forward on time and off time, dead time. We can see that dead time is not zero only in DCM, as it must be. Then we calculate the power parameters, for which we must know primary winding, primary current, mean current, secondary mean current, to calculate the output power. Reflected voltage on the switch. It is very useful to know it because it must not exceed the its rated maximum voltage, avalanche voltage, 5.5 volts, as we could see. Okay, then we have power losses on MOSFET. It is switching losses, conduction losses, leakage losses. I called leakage losses the losses which are dedicated to leakage inductance on a transformer. Capacitance losses, it means the losses which arise from drain source capacitance of the switch discharging through the MOSFET when it is open, and total power losses on the MOSFET. And then the same parameters are for transformer, primary winding power losses, secondary, total, and for the rectifying diode, conduction losses, switching losses, total losses. So, and the last four columns are the most what we made all this. It is input power of the converter, output power, efficiency, and charging time to the voltage specified in this column. For example, it takes 0 to 5 volts to charge it from 0 to from 500 to from 50 to 100 volts, etc. Then it is integrated by the lines, and we obtain the total charging time. We see that, for example, to charge our capacitance, it is 2000 microfarads to 900 volts. It takes, let us see, yes, to 900 volts it takes some about 13 seconds. It's our goal here of our calculation. Okay. Let us play something with parameters. For example, we can change on time to, for example, 10 microseconds. So we change something with timing parameter. I will not change off time because it is quite small already. 2 microseconds, it is very short on time. It is comparable already to the dynamic parameters of the switching elements. Okay, we set 10 volts, 10 microseconds in all nets. We obtain 15 and 6.6 volts seconds. So decreasing on time leads to increasing charging time. It's not obvious fact, and it is rather interesting. We can see that in this mode we have CCM until the converter, the output capacitor is charged to 680 volts, and then it goes to DCM mode with unlimited current, and we see that in this point the input and output power decreases abruptly from about 80 watts to about 40 watts. Okay, now let's set for example, we chose at first 14. Now let us set to 18 microseconds, and let's look how what influence does it have. (1605 volts). It's all the time larger than when we had 14 microseconds. Why is it so? It is so because we our converter goes to DCM mode already in 400 volts output. It is limited current now, so output power will not change so abruptly. Yes, we can see that there is not abrupt change in power, but its total value is quite little, only about 50 watts. So playing with parameters, we can obtain our maximum. It is 14 volts. It was the task which was behind me when in front of me when I started writing this calculator to calculate the values of time setting resistors, resistor and capacitor. I had a transformer with specific parameters, power switch with also specific parameters, and I should choose resistor and capacitor in some way. So with the help of this calculator, I could easily do this. Of course, it can be modified. For example, we can calculate power losses in our MOSFET and change accordingly its internal resistance, because it has some temperature coefficient, and we can, for example, in each line we can change it. Also, we can change, for example, parasitic capacitance. It is not the same in all voltages as it is here. It goes down when the output voltage, drain source voltage, increases in reality. So we can model it with more precisely. Well, I hope that this calculator will be useful for anybody. I also congratulate you again with the beginning of studying year, and wish you good luck and good health. Bye bye.